question now. The first part is the Rutherford alpha scattering experiment. Let me close this file.
0 people did this one, right?
No. A lot of people did this one. It's a good question as well. Yeah, you'll do this one in ESAP, but the experiment is actually... Can you please be quiet? Thank you. That's great. The Rutherford experiment is this. What he did was he had some gold leaf. You know what gold leaf is? It's like gold paper, but very, very thin, like a micrometer. It has many applications, yeah. So gold leaf, what you have is then the gold atoms like this. And then, guys, come on, please. And the electrons are going around the atom. Around the gold leaf atoms. I don't remember what the number is for gold, but it's not important for this. And what Rutherford did was he took the alpha particle radiation and he fired it at the gold paper. And what happens is most of the time the particle would, hit it and then bounce back. But then some of the time the particle would travel in between the gold leaf. But will it travel in a straight line? No, because what charge does this alpha particle have? Positive, 2 positive. And when it passes near the electron... No, it doesn't. No, it doesn't. The alpha particle has 2 protons, 2 neutrons, and that's it. So what's its charge? 2. So when it comes near an electron, what happens?
It gets
attracted. So its path would be deflected, in other words. Okay? Now, of course, if both electrons were at the same place at the same time, they would cancel each other, but that's unlikely to happen. So most of the time the particle is deflected. Most of the time the particle, I think, bounces back off the gold leaf. Some of the time the particle will travel straight through, and some of the time the particle will be deflected. And this is enough to give you the idea that the electron orbits the atom, because before this experiment people thought the atom looked like this. They thought it was protons and electrons and neutrons all together in the center. So when the alpha particle goes by, it's not affected because these charges they cancel. But if the electron is on the outside with the proton and the neutron, it means when it comes by, if the electron is in the right place at the right time, the electron force attracting it is stronger than the proton force repelling it. So this experiment, very simple experiment, you just fire the alpha particles through the gold leaf, but because of how the particles move, it allows Rutherford to think that the electron orbits the nucleus. And in fact, with careful calculation, he was able to calculate the size of the atom and the size of the orbit of the electron. So he was able to get a very accurate, clear picture of the shape of the atom by studying the different possible paths that were made. Okay? So I talked a lot about that. In the exam, they want a paragraph. So you would say something like, Rutherford fired alpha particles to a gold leaf sheet. Some of the particles bounced back, some of the particles travelled straight through, and some of the particles were deflected. From this, he concluded that the electron must be on the outside of the nucleus. This is the only way to make this behaviour. Now, there's many different ways you can describe it. I'm just trying to teach you the basic idea so you can write your own paragraph in the exam. And you'll do an ESAT lesson on this. Okay, the next question, I've answered it already. So he thinks the nucleus is the positive part and then the shell on the outside is the negative one, therefore where the electron lives. Right, now you said you wanted the diagram of the atom. Well, you all know what an atom looks like because you've done physics and chemistry, but Tal, you said you wanted to see the marking scheme for this one here. So it is, what version is it, please? Number 5. Sorry, Todd, it looks like the big paragraph there. Look, nucleus containing protons and neutrons, the electrons orbiting the nucleus. The atom consists of a very small nucleus containing positively charged protons and usually neutrons which have no electric charge. Well, that's what we all said. You have to say the neutron is neutral, proton positive, electron negative. Electric orbits the nucleus, they carry a negative charge, and the number of electrons is equal to the number of protons in the nucleus. It's important to say that because the question specifically said no charge. They said that in the question. Now this is just for the marker, not for the student. Please allow other possible explanations. For example, students may refer to an electron cloud around the nucleus with charge equal but opposite to that of the proton in the nucleus. So it's not as big as it looks, it's actually only this much here, from here to here. Okay, so it's not too bad. Okay, next part. Give me 2 properties of the strong nuclear, wait. Nobody say, well, okay, I suppose could say strong. Give me 2 properties of the strong nuclear force. Try not to say it's strong and nuclear. Okay, so give me 2 other things. What's that? Strong nuclear force. Well, firstly, what does it do? Yeah, so one feature of the strong nuclear force, one property is it's a force only present inside the nucleus of an atom. So I consider that a property because, as you know, other forces can be present everywhere. You know, like a magnetic force can be anywhere, a gravitational force can be anywhere, but a strong nuclear force only exists inside the nucleus of an atom. It is a strong force. What else do we know about it? Anything else? No, come on. Fairly short range. The strong nuclear force only works on a small distance. After that, it no longer has an effect. I would consider it of the order maybe 10 to the minus 10 meters. Unlike gravity, which you can feel at a great distance, the strong nuclear force, protons and neutrons can only feel them at a short distance. Anything else? Give me another property now. They asked for 2. But I want 2 good ones. I think this is a good one.
And what about the
yeah, I'd say it's okay, yeah, it's inside the nucleus, and it is the strongest of the 4 fundamental forces in nature, and only occurs inside the atom. Actually, more precisely, the nucleus of the atom. Now, I'm curious to what they wanted in the marking scheme, so let's have a look and see how we did. that's what I said. It's a very short range and it is attractive, meaning it holds stuff together. Yeah. It holds stuff together. Great. Okay. Right. So part A of this question was all description, no calculation. Some people like this and some people don't like this. What do we feel? We like it or don't like it? Don't really like this? Now, give me the B part is calculation. So, B part 1, nice and easy, balance that equation. Okay, so, what type of radiation is it? Alpha. So, we know straight away because it's alpha. At the end here, there's helium 4, 2. So that means here is 220 and this is 88, isn't it? 86. 3 marks. What? Yeah. Alright, so try the next part, please. Part here is also very easy. The decay constant, the formula is in the formula book. It's the half-life divided by log 2.
Log 2.
Sorry, I wrote upside down. Log 2 divided by the half-life time. And the log 2 is log 2, and the half-life is 3.6 days. Yeah. So what do we get here for the decay constant? 2.23 times 10 to the minus 6. What's the unit for half decay constant? Yeah, hertz. So it's, did you say minus 6?
Yeah.
So micro hertz. Okay. The next part now is what is the activity? Yes, do the next 3 parts, please. So let's have a look at this next part. So activity equals decay constant multiply n, which is 2.23 times 10 to the minus 6 times 1.85 times 10 to the 9 equals. Sorry, I'm trying to contain my anger. Equals.
4122.
Yeah, 4122. Yeah.
0.7.
Oh, there's no 10 to the anything.
No.
0.7. About. So, in other words, it would be 4120. And what's the unit for activity?
What is for
3 significant figures. Not hertz, because it's N is atoms.
BQ.
Yeah, atoms per second, BQ, yeah. Right, part 2 and 3 requires the use of the formula with the E in it, possibly. No, it doesn't actually. Doesn't. No, it doesn't. It does. Part 2 does not.
After 3 half-lives, we have 1 half-life.
Dude. Look.
Oh, yeah.
Look. What happens to the number of atoms after 1 half-life? It's half. So you have this number 3 times. So you type that in on your calculator and go divide 2, divide 2, divide 2. So in other words, divide 8. And what do you get? Hang on. No, give it to me in the same form. 0 point something times 10 to the 9 is what I'm looking for. This is after 8 half-lives. Sorry, after 3 half-lives.
0.228.
Okay. It's 8 times smaller after 3 half-lives.
activity is different now.
Yes, you're right. The activity is also 8 times smaller after 3 half-lives. But you're right, activity will change also as this n changes. Last part, you do now need the E formula. Give me the time until we have this amount.
Wait a second, please.
Okay.
Thank you.
Oh, it sounds hellish the way. I'll go ahead with this one now, yeah? So, we have 8. N equals N0 E minus lambda T. 3.65 times 10 to the 6 equals 1.85 times 10 to the 9. E minus, what was my decay constant? It was 2.23 micro. 2.23 10 to the minus 6 t. And we want the t. So firstly I'll divide 3.65 times 10 to the 6 over 1.85 times 10 to the 9. That gives me it with the e. How do I cancel the e? Log. So we have log of this equals minus 2.23 times 10 to the minus 6t. So the time would equal log 3.65 times 10 to the 6 over 1.85 times 10 to the 9 all over minus 2.23 times 10 to the minus 6. What is it?
2.3 in the
Yeah, no, okay. We'll do the days in one step as well. So this is in seconds, isn't it? So if we want it in days, we need to divide by 24 times 3,600. So what is that in days then? 32.3 days. Let's have a look at the marking scheme here. Yeah. Close enough.
Let's go.
No. I want to do a section A question. Then we'll go. Yeah. Of course. Because we have one less than that.
Really?
Oh, yes, I remember one of the pages is lost.
Go.